We've looked at alpha and beta decay, which both involve the emission of particles from the nucleus, but they also involve the emission of energy from the nucleus. And sometimes we only get energy from the nucleus. That's what gamma decay is. So it's a high energy gamma ray, which is actually an electromagnetic wave. Other types of electromagnetic waves you're familiar with: infrared, ultraviolet, X-rays, even the light and radio waves that we communicate and see with. Those are all electromagnetic waves. Gamma rays are the most energetic ones. And so that means these can cause some pretty severe damage, especially on a cellular level, because they can interact with the protons or with the electrons and the chemical bonds and start to break things apart. So when this is happening, when it's just gamma decay, you have an unstable nucleus and it's shaken, and we kind of actually think of the nucleus as having energy levels just like the electrons out here have energy levels, and these things can relax into a lower energy state, and when they do that, they give off some energy, and that energy can come out as a gamma ray. Now, gamma decay is pretty easy. Sometimes it accompanies beta or alpha decay. Sometimes it's all by itself. So this says cobalt-60 undergoes beta decay. Write the equation of the process. Well, cobalt says 60, so we can put that. That's our mass number. And then we look for cobalt on the periodic table, and we see it as 27 protons. And it undergoes beta minus decay. So beta is a -1 here and 0 for a mass number, and remember the right side has to add up to the left side, so this is going to be 28 and 60, and we look for element 28 and we see that that is in fact nickel. And then it also undergoes gamma decay, so that means there's also some gamma particles coming out. Well, gamma rays, they're not particles, so we get some energy out of this. This one says technetium-99 undergoes gamma decay alone. Write an equation for this process. This is pretty easy. We find this on the periodic table, and it's got a symbol Tc. It has got 43 protons and 99 for a mass number. It undergoes gamma decay, and only gamma decay, which means it didn't change any particles into anything else, didn't eject anything from the nucleus except energy, so we get that gamma ray out of that. So that one's pretty straightforward. And then identify the type of radioactive decay, Neptunium-239. So let's find Neptunium on the periodic table. We're told its mass number is 239. It's down below. And Neptunium has 93 protons. It's right there next to uranium. It undergoes radioactive decay resulting in plutonium-239. So we find plutonium, Pu. It has 94 protons. And this is also 239. Well, we can't just create a particle, so this side has to add up to that side. So we know there must have been a particle that came out of it. The protons changed, but the mass number didn't, so that tells us it's a beta particle. And we're going to need a -1 over here, so 94 minus 1 gets us 93. Here it is. Gamma rays are also given off, so here's our gamma rays. We wrote an equation for this radioactive decay, and we know that this is beta minus decay. It ejected an electron. So a neutron ejected an electron, changed to a proton. Mass number didn't change, but we did gain 1 proton in this radioactive decay. Another one, osmium-170. We find osmium on the periodic table, and we see that osmium has 76 protons. It is 170 for a mass number. It undergoes radioactive decay, resulting in tungsten. Tungsten's fun because its symbol is W, from the German for Wolfram, 166. And we look up tungsten, we see it's got 74 protons. Well, right away we can see the mass number change. It's got to be an alpha decay. We need 4 up here, and 2 plus 74. This is helium, that's an alpha particle. And then it says, write the equation and identify the radioactive decay resulting in this. Tell what types of radioactive decay is occurring. That's alpha decay. It doesn't say that gamma was released, so we won't include it. Now, I hope you've noticed in both alpha, beta, and gamma decay, we actually do have some conservation stuff occurring. Remember, conserved means the amount stays the same. The amount of particles in the nucleus between the two atoms or particles released So the amount of particles is actually conserved. So during radioactive decay, the number of protons plus neutrons is conserved. The mass number stays the same. So protons aren't conserved, neutrons aren't conserved, because these actually can change back and forth into each other if we're emitting electrons or positrons, but we are not creating or destroying matter. Sometimes some mass is converted into energy, right? So the amount of mass goes down, but the amount of particles does not. So radioactive decay, because of an unstable nucleus, it can decay by changing into smaller or less massive atoms, and it does that by giving away particles, and those could be alpha or beta particles, or energy, and that's gamma rays, or both. So it can do all of those things. And remember, mass is lost during a nuclear reaction, but particles are not, and that mass is lost in the sense that it's no longer mass, but it is in fact still energy. So lots of energy can come out of radioactive decay.